for the next couple of slides, I'm going to be presenting information about the SPaT data that grows across the interfaces at a signalized intersection. So my presentation is broken up into three parts. We'll first start by reviewing the actual SPaT message to try and better understand what intersection information, what signal information we can provide to travelers, whether it's a driver or a pedestrian. Then we'll review the proposed NTCIP 1202 version 3, which should be in ballot any day now, but look specifically at that standard to see how it specifically proposes to support the connected vehicle environment and SPaT information. Then we'll finally end by taking a look at some current implementations that broadcast the SPaT messages and what data they provide and how they provide it. We'll first start by looking at signalized intersections. So in the connected vehicle environment, we normally consider the following components at a signalized intersection. In the middle, we have the signal controller unit. On the right, we have a traffic management center to monitor and to control those signalized intersections. And on the left, we have a roadside unit that's sending information or exchanging information with connected devices, which may be a vehicle or maybe an application on a smartphone by a pedestrian. So when we talk about ITS standards, we're actually talking about the standards that define how the data exchange between one or more of these components and the vocabulary used to provide that data. So we'll first start off by just looking on the left by reviewing the SPaT message itself. When we talk about the SPaT message, we're really specifically talking about the interface between the roadside unit and the connected devices themselves. So the SPaT message is actually defined by the standard SAE J2735. It was developed with international community input, meaning that, for example, in Europe, they actually use the SPaT messages also to provide signal timing information. SPaT, in case you're not familiar with it, actually does stand for signal phase and timing message. So over the next couple of slides, we'll just skim through most, but not all, the information that can be provided in a SPaT message. In the interest of time, we'll only talk about those key pieces of information that agencies may be interested in providing in the SPaT message. So each of the following tables that we're going to show describe the information that are in the SPaT message. The last column actually indicates whether that information is required or is optional for when we broadcast SPaT message. The header in the information above the table, in this case message MSG underscore signal phase and timing, is a reference, so you can, if you're looking for more information, this is where you can find it inside the J2735 standard. So on this page, a single SPaT message can provide intersection status and signal timing information for up to 32 intersections in a single message. So it's not limited to just one intersection. Each SPaT message can optionally contain a timestamp, so this is the time when we sent the data, and a name for the group of intersections that might be included in that message. So for example, we might have the name DuPont Circle, and DuPont Circle may have 3 different intersections, for example. So this message is for the 3 intersections at DuPont Circle. The SPaT message can also contain regional extensions, which is something that we may define for a specific region. Be unique for a region. Remember, the SPaT message is intended to be used internationally. So a region may be Europe, for example. Europe has defined some additional data elements that they want to include in Europe. And in the future, you may want to decide to have some specific data elements for North America, though none exist right now. But in the future, that's something that we may be interested in doing. For each intersection, the SPaT message can contain an ID. It should be a unique ID and consists of 2 parts, a regional ID and an intersection ID. So we've been trying to figure out to design a schema so that we can design a unique ID for every intersection in North America. We haven't quite figured it out yet, but we're trying to work on it. Next is the revision number. So it's kind of like a message counter. The message counter gets updated, incremented every time you send a new message. Or so, and there's a international standard called ISO TS 19091, and I have the reference at the back of the slides that indicate that message count should only be incremented when the message content changes. So if nothing in the into SPaT message changes, you don't need to increment that message counter, because essentially the vehicle will say, oh, message counter hasn't changed, so the information hasn't changed, so I can really ignore the remainder of the message. So that was the intent of the message counter. There's also a status data element, which provides the general status of the intersection. So is it in preempt, for example? Is it operating properly? Is it running traffic fixed time, for example, and failure flash? And then the SPaT message also contains information about the movement, the status of each movement through an intersection. So looking at the intersection, what kind of information might we be interested in about a movement? So for a movement, we want to know, and a movement is a specific maneuver through an intersection. We want to know, are we allowed to move right now? Is it green, for example, or is it permitted, or is it yellow? And we're also interested in when do we expect that movement state to change? So is it in 2 seconds or maybe 15 seconds? So that's information that that's included in the SPaT message. And this table just provides a little bit more detail specifically. For signal group, the signal group ID is used to identify each particular movement to an intersection. We also use this signal group ID to link it to a map message. And we'll talk a little bit more about that later. But for the event state or the movement phase state, we want to know, is it a protected movement? Is it yellow? Is it red right now? Is it a flashing yellow, for example? Timing, when do we expect the time that movement to end, whether it's a red, when do we expect the red to end, or the protected green end? Interestingly, we can also provide speed information, advisory speed. So we can say, hey, for this left turn, for example, we advise that the speed be 15 miles per hour. Or we can actually provide specific advisory speeds for a specific type of vehicle. So for general vehicles, it's 25 miles per hour, but for a truck, we may want to say it's only advisable to go 15 miles per hour. This is more information about the time when the event will change. So the only thing that's required is the minimum end time. So what's the earliest time that this movement state will change? It's also possible that that time has already been passed. So we may say, well, it's going to change 3 seconds after midnight, but you might be in 5 seconds after midnight. So that essentially means, oh, well, it could change any split second now because the minimum end time has already passed. So there's other information that we can provide. Start time, when did the state first begin? What's the maximum? So what's the maximum time? The latest time that this state will end? The likely time, when do we think most likely the state will end, along with confidence? How likely do we think that likely time will occur? And next time, which is more for eco driving, for example. Oh, well, it's gonna, when will the green start up again? So for my eco driving algorithms, please note though that these are now timestamps. The earlier versions of the J2735 had time to change, meaning it's going to change, the state is likely going to change in about 3 seconds, and then a tenth of a second later, they might say, oh, it's likely going to change to 2.9 seconds. These are now timestamps. These are the times, the time we expect that that the phase state will end. That way, we don't have to send updates every tenth of a second. We don't have to worry about communications latency. So the earlier versions of the J2735, like the safety pilot, used time to change, and now the current version uses timestamps. Two other pieces of information that might be of interest in the SPaT message are something called enabled lanes and something called maneuver assist. The enabled lanes, for map messages, when we developed the map messages, it was intended that map message will rarely change, meaning the same map message should be applicable for a month, maybe years before it changes again. The only times you change the contents of a map message really are when the roadway geometry physically changes, meaning you add a different lane or perhaps you do some restriping of the lane at an intersection. So, but there's conditions where a same physical lane, maybe the use might vary by time of day or day of the week. So, for example, during certain times, a physical lane might be a parking lane or for reversible lanes. Maneuver assist helps provide additional dynamic information about a specific movement through the intersection. So now showing a graphic example, we have here a lane 1 and a lane 5. In the map message, physically they're the same lane, but in the map message we may say, hey, when lane 1 is active, it means it's being used as a parking lane. So no vehicles or should be driving in lane vehicles is using lane 1 because it's a parking lane, while lane 5 is a travel lane. So in the SPaT message, you may say, oh, during most times a day, lane 1 is active, and this will show up in the SPaT lane. So that means use lane 1 when lane 1 is defined as a parking lane. But perhaps during rush hour, we may say, okay, lane 1 is no longer active, lane 5 is now active. So that means, hey, it's no parking. You can use it as a travel lane during rush hour. So that's another use of the SPaT message. And talk about maneuver assist. You see here in lane 23, we may have a left turn allowed that goes to lane 13 or 14. So if I want to make a left turn in lane 23, I'll end up in lane 13 or 14. That's in the map message. But in the SPaT message, we may provide information about that particular movement that says, hey, there's a queue right now for vehicles wanting to make a left turn, which may be, let's say, 100 feet long. Or, oh, we've detected a pedestrian or a bicycle in that crosswalk that conflicts with that left turn movement. So it's a bit that says, hey, be careful, tells the vehicle, hey, be careful, there might be someone in that that conflicts with your left turn. So that's a second piece of information that can be included in this SPaT message. So what these really demonstrates is that the SPaT message really should be used in conjunction with the map message. The map message defines the lanes and the possible movements at the intersection. It's not expected to change unless the roadway geometry changes. The SPaT messages uses that information from the map to identify the enabled lanes, which lanes should we actually be using right now, and to provide dynamic information for a specific movement. For example, if there's a potential pedestrian or a conflict, and what key information for that movement. And both contain something called a data element called signal group ID. It's through this data element that we link the SPaT messages with the map messages. Next, I'm going to talk a little bit about NYCTV 1202. We've just started working, or actually, we now currently have a version 3 that's hopefully in ballot. What we talked about so far, we focused on the interface between the roadside unit and the connected devices. So now we're going to focus on the other two interfaces between the traffic manager center and the signal control unit, and also between the signal control unit and the roadside unit. So if you're not familiar with NYCTV 1202, it's really standard defines the data that is used between the traffic management center so that we can manage signal controllers, such as monitoring the signal controllers, monitoring status, being able to change timing plans in the signal controller. Version 3 is currently in ballot, and in version 3, we've added some systems engineering content. So instead of just being a data dictionary and with some data objects, it's like, hey, good luck figuring out what these data objects mean. We now added user needs and requirements. So you select the user needs, indicates what requirements might be applicable, and based on those requirements, we indicate what data objects and dialogues can be used to fulfill those requirements. So we also added support for a cabinet, like say, is the cabinet temperature really high, manage inputs, output mappings, exception reporting or traps, and also support it for the connected vehicle environment. So our supported connected vehicle environment consists of the following user needs: being able to configure the interface between the controller and the RSU, meaning what ports are open, what data do we want to share between the signal controller and the roadside unit. To be able to generate and exchange SPaT data, not only provide SPaT data to the roadside unit, but to also monitor what's going out in the SPaT messages at the traffic management center. The third one, being able to generate and exchange map data, was interesting. When we started out working on 12.02 version 3, we didn't expect to have this user need, but we quickly realized that we had to make sure that the SPaT data that is being provided matches the map data that's being used. If the SPaT and map data don't match up, we can cause traffic accidents at the intersection. So that's why we added that specific user need. And for the last bullet, one of the interesting benefits of the connected vehicle environment is we have a wealth of data that might be available from these connected vehicles. So we've added we support a user need so that we can get that information from the basic safety message and personal safety message and use it as detector inputs into traffic signal control. I apologize for this graphic a little. This is taken directly out of the NTCIP 12.02 version 3. In the left side between the DSRC radio and the CV roadside process, that's actually the SPaT messages that are being broadcasted. What this is really a logical architecture, meaning when we started talking about the connected vehicle interfaces, we realized that there were at least two different processes that we had to consider. One is the ASC process, which is the normal signal timing operations that we associate with a signal controller. But we also added this process called the CV roadside process, which is the connected vehicle applications, being able to generate and the SPaT and map messages, being able to receive the basic safety messages and the personal safety messages. So, and I'll show why later in the next slide, but we started looking at what data goes between these different processes, these different components. The first one we did was take a look at the traffic management center to the ASC process or the signal controller. So the data that goes back and forth includes managed ASC, meaning the basic monitoring and controlling of the the signal controller, but also being able to get from the signal controller the SPaT information, the SPaT data, so the traffic management center can visualize, see what SPaT data is being generated by the signal controller. We also looked at between the traffic management center and the CV roadside process, the CV application. With that, we wanted to at least be able to manage the connected vehicle detectors, meaning using the basic safety messages as detector inputs. Well, we want to manage those detectors, but also to monitor, hey, what map data is being broadcasted by the CV roadside process. Third, we also looked at the interface between the signal controller and the CV roadside process. So the signal controller has to be able to provide the SPaT data to the CV application, and the CV application has to be able to provide CV detector actuations, the information from the CV detectors back to the signal controller. The reason why we wrote that and created that logical architecture is because they're physically the CV process could be in different physical units. The SE process is always going to be part of the signal controller, so that's part of your ATC, for example. But the CV applications can reside in 3 different locations, potentially, depending on your vendor. It could be in the same physical unit as the DSRC radio, meaning there might be a unit out there that includes the DSRC antenna, but also contains the CV roads, the CV applications. Or some vendors, some of the signal controller manufacturers are providing, as part of the ATCs, the ability to run some of those CV applications as part of the control unit. It might be a separate card, but the idea is still the same. And then finally, there's the CV roadside process might be in its own separate physical unit. MITS, ITSS, for example, the multimodal ITS system is an example of that. You have a separate DSRC radio antenna. You have a separate Linux box that contains the CV applications, and then you have a separate physical unit, which is the signal controller. So there are three. That's why we separate the CV roadside process, because physically it might be located in different physical units. Another issue that we had to consider was, if you're familiar with NTCIP, we actually use something called SNMP, Simple Network Management Protocol. And the way SNMP works, there is a component that's considered the manager. So essentially we're asking the question, does the ASC push the SPaT data to the RSU, or does the RSU pull the SPaT data from the ASC? Each of these architectures has its own benefits or issues. Some of them are related to security, part of it's complexity, and it may be determined by the policies of each agency, but we didn't want to define it or make a stand in NTCIP 1202. So we support both both ways. We decided let's let the market decide as it matures, figure out which is better for the manager, which is the better physical architecture, which is preferred. So both of these should be really defined in your specification when you specify how you implement your SPaT, how you implement your SPaT messages. So just to give a little bit more information about 1202 version 3, talking a little bit more detail. So we talked about 4 user needs. One is to configure the RSU interface, so that's managing the ports, managing the watchdog, being able to generate and exchange SPaT data. All the objects related to SPaT in 2735 2016-03, which is the current version, we created objects to address all the mandatory and optional data elements with 2 exceptions. One is the start time for movement. Even within, remember, because this is an international standard, there's some ambiguity on what is meant by start time. So we did not include that in NTCIP 1202 version 3. And regional extensions we currently don't support because none has been defined for the North American region. We also add some performance requirements, so you can specify how often the SPaT data provided and how quickly is SPaT data provided after the event, meaning something changed, how quickly do we to get that information out to the RSU. Generate and exchange SPaT data, there is some issues. One of the big issues that we're trying to, that you have to be aware of is the time reference. Your clock on the signal controller may be different from the clock on the roadside unit. The roadside unit should be using, in North America, the global positioning system, but your signal controller may be using a different time source, let's say the Eastern electrical grid, for example. So in NTCIP 1202, the controller provides its timestamps in ticks. We don't say seconds, we use it in ticks, which is equivalent to 1/10 of a second. That allows the RSU to resolve the time, figure out, what is the time differences, and then sends out the SPaT data with the correct timestamps. We also, the third user need was to generate a map data. Like I mentioned earlier, we created objects. We needed to make sure, we wanted a way to make sure that SPaT data and the map data is synchronized. If you're providing SPaT data and broadcasting a different map, that's a problem. So we created objects to support all the mandatory and most of the optional data elements for intersection in J2735. And in 1202, we added some objects to provide a check that the current map is being broadcasted or let's see, what's the right word? A valid map is being broadcasted, but also provide a check that mutually exclusive enabled lanes are not in effect. And finally, we also added objects to support the basic safety, to use basic safety messages and personal safety messages as detector inputs. We essentially create virtual detectors with boundaries that can be defined as a lane or geofence, and we can use any basic safety message or personal safety message within that boundary and use it as an input into a detector. So, for example, if your signal controller supports 64 detectors, we might be able to use messages or vehicles on that's within a specific boundary as a input into detector number 63, for example. Just some final notes. I mentioned a signal group ID that's used in the map and SPaT messages. In 1202 version 3, we make that equivalent to a channel output number. So if you have an output and channel output number 10, that's equivalent. We made that equivalent to signal group ID number 10. We thought about using the phase numbering, but with the overlaps and pedestrians, we decided that was really difficult. So we made it equivalent to the channel output. 1202 version 3 should be in ballot any day now. Some vendors have started adopting the balloted standard. Note that there is some risk involved. If you try to use 1202 version 3 right away, it's still subject to changes until it gets published. And since we haven't really implemented all 1202 version 3, there's still some lessons learned that we don't have right now. I'm just going to spend 5 more minutes talking about some of the SPaT implementations that currently exist. First is New York City CV Pilot. They've made the decision to implement the ballot version of 1202 version 3 to provide SPaT data. So they've been working with the ASC working group on implementation issues. Because now day 2735 is timestamps, they only send SPaT data to their RSUs when there's a change in the movement status, whether it's the state or the timestamps. Because it's timestamps now, they also spend the SPaT data to the Amazon cloud to support pedestrian applications for the visually impaired. In the New York City CV Pilot implementation, the RSU will then translate the SPaT data that's received by the signal controller and generate the SPaT messages using the SPaT data to the timestamps in the SPaT data to make the changes so that the SPaT messages provide the correct timestamps. They've taken lots of effort to look at the security as a whole, so their security design for their implementation considers the RSU, the signal controller, and the TMC as a whole system. And because now we're using timestamps, so they don't have to send out, the signal controllers doesn't have to send out SPaT data every tenth of a second. It just opens up the channel usage, so there's more wireless channel, more communications time available for other messages. The Tampa CV Pilot, they're using Siemens SPaT Map application, which is part of Siemens core RSU software. But instead of using the NTCIP 1202 version 3, they're using the SPaT message that's defined in the V2I Hub interface control document that Chris Stanley will talk about a little bit more in detail right after me. So that defines messages or data objects that can get exchanged between the signal controller and the RSU. So it's an alternative method, a second method that can be used. They are using some other functions that's provided by MITS, such as signal priority, but otherwise they're using their own SPaT Map application, which takes the SPaT data from the signal controller and resolves it with the map data that's part of their application. And finally, with MITS, their current version of MITS has a roadside processor between the signal controller and the RSC radio, so it's a third physical unit between them. They are using the Patels SPaT message blob, which consists of NTCIP 1202 version 2 objects with some additional objects that have been defined between the roadside processor and the signal controller. It is based on the 2009 version of the SAE J2735. So SPaT, so it's not timestamps, it's the time to change. So has to be sent every tenth of a second. They've started working on, or they're about to start version 2. They haven't made the decision yet, but they're considering using the NTCIP 1202 version 3 object definitions. In summary, the industry still is transitioning to support SPaT. We are still working, the SRC Technical Committee is still working with different implementations to see what issues we're finding with the SPaT data, including Europe, including North America. But the current options between the RSU and the controller. There's really two options right now. One is the ballot standard of 1202 version 3, which again has its risk. It hasn't been proven yet. But there's also the interface control document that's defined in the V2I hub. My best opinion or suggestion right now is really talk to your vendor provider for the signal control, see where they are with 1202 version 3 or what they recommend and work with them. And finally, I have 2 or 3 more slides about resources if you're more interested in finding about the standards, the CV Pilot, MITS, or the ISO TS 19091. Thank you very much for your time. Chris?